This conference will now be recorded.
Yeah, in the last session, we have discussed about definition of the probability, how to define the probability in conditional way, and the other way, that is using relative frequency. And at the same time, we have seen different properties of probabilities and how to find the probability for any application is discussed in the last class. And now we are going to discuss about conditional probability. So in the name itself, conditional probability, in the sense, here the occurrence of one event is depending on the other event. If at all, if occurrence of one event is depending on occurrence of other event, we can define the conditional probability. For example, here, if I have two events, let me take the events as event A and event B. Then you can represent or you can denote the conditional probability as P of A given B. That A slash B must be read as A given B. So in the sense, the event A occurs depends on the event B, occurrence of event B, right? A simple example here. A student coming to the class is depending on the bus coming to the college. So that is always the probability of the student coming to the college is depending on the probability of bus coming to the college. So that is here event A is nothing but the student coming to the college. Event B is nothing but the bus coming to the college. So here it is, there you can decide the presence of the student based on the presence of bus, right? So here in that way you can define the conditional probability, and mathematically you can define the conditional probability as P of A given B equal to P of A intersection B. In the last session we have seen what is P of A intersection B. P of A intersection B is nothing but the joint probability of A and B. P of A intersection B by P of B, where P of B greater than 0. If at all, if the probability of B is 0 and the conditional probability does not exist. And that is, in the same example, if at all, if the probability of bus coming to the college is 0, and definitely we cannot define the conditional probability, right? And another condition is if P of A intersection B is 0, ultimately the conditional probability also will be equal to 0. That is, if at all, if the joint probability is 0, the conditional probability will be equal to 0, right? In the other way also you can write the probability of B given A can also be written as P of A intersection B by P of A. In fact, we should write it as P of B intersection A. And anyway, P of A intersection B is absolutely equal to P of B intersection A. Therefore, you can also write the definition for P of B given A as P of A intersection B by P of A. And this is the conditional probability of an event B when given event A. This is the way to define the conditional probability, right? So here we can also write the joint probability in terms of conditional probability by using the previous expression. That is P of A intersection B equal to P of A given B into P of B. Or we can also write P of B given A into P of A. In the sense, if any conditional probability is known, you can find the joint probability. Or if you know the joint probability, you can find the conditional probability. And that is the relation between conditional probability and joint probability. Here, if you observe, we have written the conditional probability as transition probabilities. So why we are saying them as transition probabilities? And that part we'll discuss while discussing about Bayes theorem, right? And if at all, if the two events are mutually exclusive events, in the sense there is no dependency of A on B. That is, the student is not coming by bus. Ultimately, the conditional probability does not exist, right? So if at all, if there is no dependency of event A on event B, that is, if A and B are mutually exclusive, or the intersection of the two events is a null set, then the conditional probability becomes 0, right? So here, when the conditional probability becomes 0, if at all, if the event A is not depending on event B, or if the intersection of the two events A and B is giving null set, then the conditional probability will be equal to 0. This is all about conditional probability. So let us take one simple example, then you can understand better. And let me take a problem, and let me take an example, that is rolling a die experiment. In the last class, the last session, also we have discussed about some application of rolling a die experiment, right? So similar experiment I am taking, and I am just rolling a die. So here, so you are asked to roll a die and observe the number. So what are the possible values you have when you roll a die? 6 possibilities, right? So let A be an event which is odd outcome, and B is at least 4. At least 4 in the sense it may be 4 or 5 or 6. That is called at least 4. Then what is the probability of A given B? A given B, in the sense, if B is occurred, what is the chance of getting an event A? I repeat, if B event is occurred or achieved, what is the probability of achieving or getting the event A? How do you find? Yes, by using the previous relations you can find. First, what are the events taken here? A as odd outcomes. Odd outcomes in the sense 1, 3, 5. I said, as I said, B is at least 4 in the sense 4, 5, 6. And ultimately here, the A intersection B is equal to 5. So when 5 is occurred, then ultimately you can say the two are satisfied. So therefore, the probability of B is equal to how much actually here? So I need to find what? P of A given B. So as per the previous relations, we know that P of A given B equal to P of A intersection B by P of B. So we need to know the probability of P A intersection B and probability of event B. So therefore I am writing now first probability of event B. What is the probability of event B? As event B is 4, 5, 6. Out of the 6 outcomes, possible outcomes, here we are expecting any outcome that is from 4, 5, 6. So what is the chance of occurrence here? Ultimately 50%. The number of outcomes or number of elements in the event B are 3. The total number of elements in the sample space are, the total number of possible outcomes is 6. So therefore 3 by 6. Therefore P of B equal to 1 by 2. And also we are supposed to find P of A intersection B. So what is P of A intersection B? Probability of occurrence of number 5 on a die, which is equal to 1 by 6. Why? Because each and every number will have equal probability in the rolling a die experiment, and each number will have the probability equal to 1 by 6, or the number of elements in the event A intersection B is 1. The total number of elements in the sample space are all the possible outcomes are 6. So therefore 1 by 6. Therefore, what is the conditional probability? P of A given B equal to P of A intersection B by P of B, which is equal to 1 by 6 by 1 by 2. The resultant is 1 by 3. Right? So this is the way to calculate the conditional probability. And let me give a simple application here, and you are supposed to give the answer for this, right? So here I am selecting two bowls. So one bowl is A, another bowl is B, and bowl A is having one blue marble and four yellow marbles. Bowl B is having three blue marbles and two yellow marbles, right? So when I select marble, blue marble from the box A, what is the probability? And yellow marble from the box B, what is the probability? That you need to find, right? So I repeat, and we have taken two boxes, and the two boxes are with two different colored marbles, and the first box is having the combination of blue and yellow, second box is having combination of blue and yellow, right? So there you are supposed to find the conditional probability. Okay, right? Next, another thing we are entering is total probability. So here the total probability will come into the picture whenever any event is depending on more number of other events. More number of other events. For example, here the same example, classroom example I am taking, but in the different way, right? The student coming to the college on time is an event. The student coming to the college is an event, right? So let us take an example, that is the student is coming to the college every day from the home by different means. The first thing is, he is always every day he catches an auto at the home until he reaches the bus stop, RTC bus stop. And at the RTC bus stop, yes, that is every day he catches the RTC bus to reach the college bus stop. And at the college bus stop, he catches the college bus and he reaches the college, right? So that is, he is using three means of transportation. One is auto, other one is RTC bus, and the third one is college bus, right? So here, what is the event here? The student coming to the college on time is depending on how many parameters here or how many events here. First event is auto coming to the home on time, first event. Second event is RTC bus coming to the bus stop on time. Third event is college bus coming to the bus stop on time. So that is, he is the event A. If I suppose that is if I assume the student coming to the college on time as event A, and auto coming to the home on time event B1, and RTC bus coming to the bus stop on time event B2, and college bus coming to the bus stop on time event 3. Here event A is depending on event B1, B2, B3. Then ultimately here we need to take are the probability of that particular student coming to the college on time depends on all the events. There you are supposed to take the total probability by taking the conditional probabilities of A on B1, A on B2, A on B3, right? But here, for example, total A1, A2, A3, A4, A5, A6. 6 events are selected in the sample space. But in the live example, I have taken only 3 plus 1, 4 examples. Here 6 examples are selected, right? Now, total probability. If B is any event within S, then we can express B as the union of subsets. That is B intersection A1. So in the previous example, I have taken A, B1, B2, B3. And now if I take it as the notation as B, A1, A2, A3, A4 up to AN, if at all, if n number of events are considered, right? So here B is equal to B intersection A1, the joint probability of B and A1, that is student and R2. Next, joint probability of student and RTC bus, and joint probability of student and college bus, right? So like that, we can take the event B as the intersection of B A1 union, intersection of B A2 union, and so on. Finally, what I can write is the probability of occurrence of that particular event is equal to probability of occurrence of the joint probability plus B and A1 plus the probability of occurrence of joint probability B and A2, and so on. So that is the way to define the total probability of any event B, if at all, if that B is depending on the other events from A1 to A, right? So that is the way to define the total probability. Fine. Or else you can also represent the total probability using conditional probabilities. Conditional probabilities. How do you define? We know the relationship between the joint probability and conditional probability. The same can be substituted in the expression of the probability of event B. So therefore, how do you write? P of B equal to P of B given A1 into P of A1. Why? Because P of B intersection A1 is P of B given A1 into P of A1. Similarly, P of B intersection A2 is P of B given A2 into P of B2, and so on up to the nth event, dependency of nth event, that is probability of B given An into P of An. That is the total probability expression for any event B which is depending on n number of events from A1 to An, right? So it is a very important equation in the analysis of real-time experiments, right? Or else in the short form, you can write it as in the form of summation I equal to 1 to n P of B given AI into P of AI. That is the final expression for total probability of any event B which is depending on events A1 to AN. Fine, right? This is called total theorem of total probability, right? And the next, a very important thing is Bayes, and the Bayes theorem plays a major role in the real-time applications for finding conditional probabilities. Bayes theorem plays a major role in almost in all the scientific applications and engineering applications, especially in the communication applications, for finding the conditional probabilities. Simple example here. So here, where do I need to use this conditional probabilities, or where do I need to use this Bayes theorem? For example, I have an application, simple application. So here I have two transmitters, that is two members are transmitting some signal, digital signal, right? And at the same time, at the destination point, I have two receivers, two transmitters and two receivers. And the two transmitters are sending the signals, two receivers are sending the signal. And usually here, and let me take this as B1 and B2. This one as in the receiver section, let me take the receiver antennas are A1 and A2. So here these people are sending the transmitting the signals, digital signals. These people are receiving the signals. After receiving the application, after receiving, then the A1 doesn't know that whether the signal is transmitted by B1 and B2. If it that scenario, to find after receiving, to find the probability that the signal is transmitted by A1. If the B1 is receiving the signal, what is the probability that that signal is transmitted by A1? Otherwise, if the signal is received by the B1, what is the probability that the signal is transmitted by A2? Like that, I need to find the probabilities. I need to find the probabilities after the experiment is finished. What is the experiment here? Signal transmission is an experiment. And once the experiment is finished, I need to find some probabilities to check the errors. Why? Because here the transmission or the communication system is established in such a way that, and whatever the signal transmitted by the A1, that must be received by B1, and whatever the signal transmitted by A2 must be received by B2. In such a way, the communication system is established. For example, here, if A1, B1 is receiving the signal, it doesn't know whether it is transmitted by A1 or A2. And if it is transmitted by A1, absolutely the communication system is established in the perfect manner without error. If it is transmitted by B2, B2, then ultimately you can say there is an error. And in the real time, we cannot say the error is absolutely zero, and we need to minimize while establishing the communication system. Therefore, we need to check the error probabilities while establishing the communication system, and so that by minimizing that particular error probabilities, you can establish the communication system with more accuracy, right? So, and there we take the help of Bayes theorem, and Bayes theorem is used to find the conditional probabilities in the applications, right? For example, conditional probability, just now we have studied, and what is conditional probability, right? Let me take the same equation here. P of A given B equal to P of A intersection B by P of B, right? And if we use the theorem of total probability to replace B, replace B. So just now we have read the total probability theorem, theorem of total probability, that is P of B, right? If I substitute that P of B, that P of B can be written as P of B given A1 into P of A1, P of B given A2 into P of A2, plus up to P of B given AN into P of AN. So that is the expression for P of A given B in terms of joint probability and the conditional probabilities, right? So that is another time. If I substitute the expression for P of A given B and substitute in the expression P of A given B, we know that P of A intersection B or P of B intersection A is also equal to P of B given A into P of A into P of A. So if I substitute, so we get what? P of A given B, which is equal to P of B given A into P of A. So I'm just doing here simple substitution. That is, I'm just eliminating the joint probability to represent the conditional probability P of A given B in terms of other conditional probabilities. In terms of other conditional probabilities, right? So this particular relation is called Bayes theorem. This is true for any event A, and so replacing A with AI you can take for multiple events. I repeat, P of A given B equal to P of B given A into P of A by the total probability of P of B. If B is depending on more events from A1 to AN, then you can write the total probability as P of B given A1, P of A1 to P of B given AN into P of AN, right? So finally, what is the Bayes theorem? P of A given B equal to P of B given A into P of A by P of B given A1 into P of A1 plus P of B given A2 into P of A2 and up to P of B given AN into P of AN. And if I substitute A in the place of A and I can write the generalized statement, it is applicable for all the events from A1 to AN. That is P of A given P can be represented as P of P given AI by into P of AI by the total probability of B, that is P of B. Fine. So it is called Bayes theorem. And what is P of AI and P of AI given B? That is here just simple example here. In the previous case and in the previous slide before entering into the Bayes theorem, I have taken a live example in the communication system. That is, what is that example? Transmitters and receiver. And here first, while analyzing the communication system, we should know the basic behavior of the transmitting antennas or simply transmitters. Whether that particular transmitter is able to send the signal or not must be known. Then only you can analyze the communication system or analyze the received signal, whether it is transmitted from B1 or B2, right? B1 or B2. So that is before the experiment is done. Which type of experiment? Transmission of signals experiment is done. We need to see the behavior of the transmitters and we need to know the probabilities of the two events or two transmitters, and these two probabilities are called a priori probabilities as they are calculated before the experiment is done, before the experiment is done. And P of A given B are called a posteriori probabilities. A posteriori probabilities, that is once the signal is received, for example B1 and B2, two transmitter, A1 and A2, two receivers, right? And probability of B1 transmitter B1, probability of transmitter B2 are known. These two are a priori probabilities. And once the signal is transmitted, and here any of the receiver is receiving, the transmission process is done. Transmission process is done. But here in the section, receiving section, that is the signal is received. After receiving the signal, if you find the probability after receiving, that is condition, that is the probability of the transmitter after received by the receiver is called a posteriori probability, right? So here in the generalized statement, P of AI are called priori probabilities, P of AI given P are called posteriori probabilities. Simple example in the animation way. So here we know that P of B into P of A given B can be taken as P of A and B, or which can also be represented as P of A into P of B given A. So if I take A and B as two events, it is P of A, and similarly here I can take P of B when given A part, a path, right? And similarly I can take this side, left side also I can take the same, but here P of B is the below one probability and P of A given B is this one. But if you observe the two portions, but one is vertical, other one is horizontal, but both are same. But both are same. So therefore, this relation is valid for all A and B. And if you know one conditional probability, you can find the other conditional probability, right? Simple example. At a certain university, 4% of men are over 6 feet tall and 1% of women are over 6 feet tall. 4% of men in the sense out of 100, 4 members are tall, 6 feet tall, and 1% in the sense out of 100, 1 woman is with 6 feet tall. The total student population is divided in the ratio 3:2 in the favor of women. So total population is divided in the form of 3:2. That is, out of 5 students, if you select, 3 are female students, 2 are male students. Why? Because read the problem carefully. The total student population is divided in the ratio 3:2 in the favor of women. Therefore, 3 are women, 2 are men out of any 5 students. In such a, that is, if I have 100 students, 60 students are female students, 40 students are male students, right? And if a student is selected at a random from among all those over 6 feet tall, I have a classroom with 100 students. Let me consider as general number 100, and out of 100, 60 are women, 40 are men. And again, in the same class, 4 members are tall. That is not 100. If I take 200, better you can understand 2 to 300, or let me take 300. So in the 300, 3:2 in the sense 300, 3:2 in the sense 180 students are female students and 120 students are male students. And out of which 4%, that is 4 3s are 12. 12 students are men with 6 feet height and 1% in the sense 3 are women with 6 feet height. So now I'm supposed to select a student, and that student is who is that student? The student with 6 feet height. What is the probability that the student is a woman? Student is a woman. That is the question. So that is what I'm supposed to find here. After selection, you are finding the probability of some event. I repeat, after selection, you are finding the probability of some event. That is, the student is a woman. So what is the event here? Selection is an event. student is a woman is a event, right? So here, how do you solve this problem? First, what is the given data? Given data, probability of men is given 4%. Probability of women is given 1%. Sorry, tall women 1%. Right? So see here. First, let us assume event M as student of male student, event F as student is female student, right? And T is an event that is student is over 6 feet tall. So what are you supposed to find here? After selection of a tall woman, what is the probability that the selected one is female? So that is, I repeat, after selecting the tall one, what is the probability that the selected one is woman or female? That is, you are supposed to find what? P of F given T. P of F given T. After T is happened, after T happened, what is the probability that F to be happened? F given T. So we know that from the previous Bayes theorem relation, P of F given T equal to P of T given F into P of F by the total probability of P of T, right? So now, therefore, we are supposed to find first P of T given F and then P of T given M, and the given data is already there. P of F is given, P of M is given. What is P of M? 2 by 5. Why? Because the ratio is 3:2. And P of F 3 by 5. Ultimately 60% chance, as we have 3:2 ratio. And right, and P of T given M already given. That is, if the many selected, what is the probability that is going to be tall? 4% chance. Therefore, 4 by 100. Similarly, ultimately female to be tall is 1% chance, that is 1 by 100. Therefore, by using the Bayes theorem, by substituting all these values, you can find out the probability of F given T. That is the way, to find the conditional probabilities in the Bayes theorem. And in the applications, especially in the probability applications, always the given problem is a very important, and you have to read twice or thrice. The total problem must be read twice or thrice. If you understand the problem, the solution is very easy, right? Another example. So let us try this one. A company producing electric relays has 3 manufacturing plants producing 50, 30, and 20%. 50%, 30%, 20%. Out of 100, 50 are by, let us say, A1. 30 are by, let us say, A2. 20 are by, let us say, A3 of its product. Suppose that the probabilities that relay manufactured by these plants is defective are 0.02. That is, if it is, that is from the manufactured units of first, that is A1, the probability of the defective one is 0.02. If I select any defect, relay, that is, that maybe belongs to the first one, but the probability of that maybe is 0.02. Similarly, that maybe from the second one, but the probability is 0.05. And similarly from the third one, 0.01 respectively, right? So if a relay is selected at random from the output of the company, what is the probability that it is defective? It is defective. How do you calculate? Let us assume the defective one, probability of defective one as P of B. So that is P of B is depending on how many events? It may be from A1, it may be from A2, it may be from A3. In other sense, if A1 is manufactured one relay, that may be defective. If A2 is manufacturing a relay, that may be defective. If A3 is manufacturing a relay, that also may be defective. Therefore, what is the total probability of the electric relay may be defective from the manufactured unit? Therefore, the total probability of defective electric relay can be taken by considering all the conditional probabilities, that is, probability of defective one when A1 is manufactured, and probability of defective one when A2 manufactures, and probability of defective one when A3 manufactures, right? So by knowing all these, you can find the total probability, right? And second question is, if a relay is selected random is found to be defective, what is the probability that it is manufactured by plant 2? That is, you have to find P of A2 given P. The defective one is selected, and what is the probability that that is manufactured by the A2? Therefore, P of A2 given P must be calculated. You do it? Yes. See there. The total probability of defective one can be taken as sum of P of P given AI into P of AI. We all know that P of P given A1 is 0.02, P of A1 is 0.5, P of B given A2 is 0.05. And substituting all these values, you are going to get the resultant probability of defective relay is 0.027. Second answer, P of A2 given B, we know the relation P of B given A2 into P of A2 by P of B, which is equal to 0.556. Like this, you can do the problems by using Bayes theorem and total probability theorem, right? Another example, simple example. An elementary binary communication system consists of transmitter that sends. So here pictorial explanation is given. Let us see. So B1, B2 transmitters. Just now I have taken the example in the very first case while explaining the Bayes theorem, right? Elementary binary communication system. What do you mean by elementary binary communication system? Binary in the sense it can transmit either 1 or 0. Binary in the sense only two possibilities, 1 or 0. Binary communication system consists of a transmitter that sends one of the two possible symbols, that may be 1 or 0, or a channel to the receiver. The channel occasionally causes an error to occur so that a 1 shows up at the receiver as a 0 and vice versa. And then find all the conditional probabilities. All the conditional probabilities in the sense, what are you supposed to find? What are the given values now? P of B1 is given. P of B2 is given. I repeat, P of B1 and P of B2 are nothing but a priori probabilities. A priori probability. And we are supposed to find what? P of A1 given P1. P of A2 given B2. P of A1 given P2. P of A2 given P2. So what are the correct probabilities here? P of A1 given B1 and P of A2 given P2 are correct probabilities. Values given as 0.9. P of A2 given B1 and P of A1 given B2 are error probabilities. They are given as 0.1. Find all the conditional probabilities in the sense, what are you supposed to find? After receiving, you are supposed to find. That is, after occurrence of event A1, what is the probability that that is sent by P1? That is, P of P1 given A1, P of B1 given A2, P of A1, that is B2 given A1, P of B2 given A2. Must be no. Must be no. Right? Solution. A1. First, what are supposed to find? I need to find P of B1 given A1, P of B2 given A2, P of B1 given A2, P of B2 given A1. So to know all these, I need to find first P of A1 and P of A2. Therefore, I have calculated first P of A1 and P of A2. By substituting that, I have calculated all the conditional probabilities. Just right. So it is the best example for communication application, binary communication channel establishment using Bayes theorem, right? Thank you. Another one is independent events. So another one is independent events. Independent events in the sense that is when you can say the two events as independent. So only you can say the two events as independent if P of A intersection P is P of A into P of P. That is the condition for the two events A and B are said to be independent, right? So if P of A intersection B equal to P of A into P of B, what happens to conditional probability? And definitely the conditional probability can be represented as P of A given B equal to P of A intersection B by P of B. If I substitute this, ultimately P of B gets cancelled and the resultant is P of A, right? So like this, you can write the relation if the two events are independent, right? And for the independent events, we have some other relations. And if there are more number of events in any experiment, if the three events A, B, C are independent, you can also write P of A intersection B intersection C equal to P of A into P of B into P of C. Similarly, the individual relations also can be taken, right? If there are more number of events, also the relation is valid from A1 to AN. To distinguish between mutual, so what do you understand? That is mutual exclusive and independent. So in the while explaining conditional probability, I've taken the example that is mutual exclusive event. Mutually exclusive in the sense A intersection B equal to pi. There is no dependency of A on B. But here, the careful consideration required here, that is, independence is different, dependency is different, mutual exclusiveness is different, independence is different. That is the major criteria you need to follow while analyzing the probability models, right? So here, therefore, I have just kept this particular slide to differentiate the two things. One is mutual exclusiveness and the other one is independence, right? So we all mutual exclusiveness in the sense P of union of AI equal to summation of individual probabilities, whereas here independence in the sense ultimately product. That is the basic difference between mutual exclusiveness and independence. This you need to remember while analyzing the problems. Exercise problems are given and you just go through the exercise problems and these becomes assignment problems. So here some assignment problems are having drawing a card or throwing a die experiments. So therefore, first you should know the basics about the playing cards and dice, right? So the total number of playing cards that you can find in a pack is 52, and the total 50 out of total 52 cards, you can find 4 symbols. That is 13 cards will be with the symbol club. First symbol is called club, and 13 cards will be with the symbol spade, and another 13 cards will be with the symbol heart, and another 13 symbols will be 13 cards will be having with the symbol diamond, right? 13 cards with club symbol, 13 cards with spade symbol, 13 cards with heart symbol, 13 cards with diamond symbol. And the 13 cards, each and all the 13 cards will be numbered from A to K. A, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Q, K. That is the sequence of cards. Right? This thing you need to remember while solving the problems related to drawing a card from the pack of playing cards. Right? These are the symbols. Fine. And sometimes A will be called as ace, K will be called as king, Q as queen, J as jack. Right? So it is all about dice. And some questions are posted here, and this will be posted in your assignment folder, and you are supposed to solve all the problems. Right? So with this we conclude the probability part in the first chapter of the PTSP subject. And in the next session we are going to see about random variables. Right? Thank you.